Do you at all mention about invalidated iterators today? Or no?
No, it's not in the slides.
Okay.
Yeah, right, that's the thing.
Okay. No worries. If there's time at the end, maybe you can mention it. Otherwise, I'll start next time. I'll just do like a quick example of like suppose you're removing stuff from a vector. Yeah.
Yeah, maybe we can do it inside one of the examples.
Okay. All right. I'm ready. Here you go.
Thanks, Avery.
Yeah. So just your swipe and it looks like that.
Perfect.
Yeah. The two files are there, right?
Yes, that's it. Hello. All right. Okay, so it is 1:30 and we are starting without any display issues. Woo! Thank you to our lovely Avery over here. Okay, so the game plan for today is we're pretty much going to be wrapping up the first two parts of the STL. We're going to finish off containers and finish off iterators. And then the last two parts, functors and lambdas, we'll actually talk about the lecture after next. And next lecture, we'll be talking about templates, which is really where all of the different pieces of the STL come together. So to start off with, just for a brief recap from last time, Associative containers, so far we've discussed sequential containers like vectors or decks. In last lecture we discussed associative containers like maps or sets. And the difference is that associative containers, instead of storing data in a sequence, they associate some sort of key data with some sort of value data. And so we have the same familiar syntax for maps and sets. And then we also learned about last time this concept of iterators. And once again, so the syntax of iterators really boils down to these 4 parts. So can someone tell me, how do we create an iterator? What is one function that creates an iterator that we learned about last time? Anyone remember? If not, I'll give this first one for you. We're still getting back into the groove. Yeah, so the way that we create an iterator traditionally involves something like calling the .begin function on a container. So in this case, remember that the type of an iterator is actually sort of logically std set of integers, : iterator, the name of the iterator, and then to create an iterator, in this case, we use the .begin. There are other ways to create iterators, such as the .end function that we also saw, and then we'll see ways to create iterators from these 2 functions later on today. Who remembers, how do we dereference an iterator? Raise your hand. Yes, go for it. Asterisk, exactly, very nice. So if you're familiar with pointers, this might seem sort of familiar. We'll actually talk at the very end of lecture today the difference between a pointer and an iterator. So just keep that in the back of your mind. But absolutely. So by dereferencing it, what it does is it follows this iterator finger and reads out the value that that iterator was pointing to. And Avery actually came up with a really good analogy for iterators after last lecture, which is that if you've ever seen Toy Story 4, or even if you haven't, and you're familiar with sort of, there's a claw machine that goes down and picks up different items, that's actually pretty much what an iterator is. You can think of an iterator as the claw itself, and then dereferencing it makes it actually go down and pick up the item and return it back to you. So if that helps you, all credits to Avery Wong over here.
I just wanted to mention, I also suggested putting the video on there, and then like putting a movie clip, and it was rejected.
That's true. Maybe at the end of class when we have time.
Next time.
Advancing an iterator. So sort of familiar syntax, we can use either iter ++ or ++ iter. Again, that's called the postfix and the prefix operators. When they are used alone, just as like a single line, the 2 are equivalent essentially. But it turns out that the ++ iter is slightly faster, and so in C++ style, we traditionally tend to go with that when there's no difference. And then finally, how do we compare against another iterator? Turns out we can use the == and the not equals comparison symbols. And one of the most common things we'll be comparing to, especially when we're working with loops, is this container.end function. Does this feel familiar? Does anyone have any questions? Okay, cool. All right. So why are iterators so cool? I'll be devoting the next couple slides to just talking about that and reminding ourselves of why. So again, sort of that's the syntax of how to use iterators. But what iterators sort of operationally do, what you can think of them doing, is taking any sort of representation of data, whether that is a vector, a set, or a cloud, or whichever. Iterators let us take that representation of data and view it in our code as though it was a linear collection of data, meaning that it will always guarantee that it'll output it in the same order, and furthermore, that it'll output it in a sorted order based on some sort of sorting function that we give to it. And once again, I covered this at the very end of class, but that is so cool because that means that when we have just a single logical idea, something like sorting a data collection, then previously, before we knew about iterators and next lecture templates, what we would have to do was implement that sort function individually for each of these different types of containers, because a vector is stored differently than a set is stored. So to be able to sort of sort them, you would have to know how they work under the hood. But what iterators allow us to do is that they give us this syntax right here, that for loop, which allows us to say, regardless of whatever container I pass into it, I know that that line of code will always work because iterators work across every container that we've learned. So just to demonstrate, this function, what it's doing is it's taking an element and counting how many times it appears in that data structure. So in this case, it's counting the number of times an element appears in a vector. In this case, it counts the number of times an element appears in a linked list. In this case, it counts how many times it appears in a set, and so on and so on. And notice that the only thing that changes is the type, and nothing about the logic. And so when we learn about templates, we'll see how we don't even have to change the type, which is kind of crazy. But that'll be next lecture. Awesome. Yeah, does anyone have any questions about sort of basic iterators? And today we'll be learning more. All right, I'm seeing some shaking heads. That's good. Okay, so before we sort of go on to explore a little more, so far we've sort of really only learned about iterators in the context of like starting at the beginning of a data structure and then sort of plussing until we reach the end. Of course, you might already know that iterators are actually useful for much more than that, so we'll be exploring that today. One other sort of tricky detail that we want to bring up is map iterators. So up to this point, so before we dive into that, we just want to reintroduce this one class. Avery mentioned it at the very end of his types lecture, but we'll go over it again because it was sort of quick. The context that we brought this in before was the idea of when we want to return multiple things from one function, before we had no way to do that besides sort of passing things in by reference and then modifying them within the function. But now, with something known as a pair, we were able to return a pair of things. So for example, if we had some sort of struct called time, then in a function we could return both the hour and the minute in the return statement. And so that's sort of what a pair has been used for so far. Syntax-wise, the way you declare it is just like any other class in C++. The std pair, the two types of the pair, and then you can access it and set the values using p.first and p.second. So you might have seen that before. Turns out, so when making this example, I searched up, what is Stanford's phone number? And there's actually a phone number for Stanford. I have no idea what that means, but if you ever happen to call that, I'd be very curious to know what it leads to. Is it Leland Stanford? Is it the president? Who knows? All right, so there's a couple other ways to make a pair, actually. Sort of the one that we traditionally learned is this one up here called uniform initialization. There's actually one other way to make a pair, which is called make pair. The difference is kind of subtle, but the difference is pretty key, which is that with make pair, you don't have to know the types ahead of time. And this will be very useful when we start working with things like templates where we won't know the types ahead of time. So sort of two different ways to make a pair. And that's sort of another way, another place where the keyword auto is actually really useful. So bringing in all of these concepts from previous lectures. And another thing that we're bringing in, so last lecture I mentioned this idea of multi-maps, which again, there's sort of three different types of characteristics that we can change when we're thinking about associative containers. We have maps, sets, we have unordered maps, unordered sets, we have multi-maps, multi-sets, and then unordered multi-maps and unordered multi-sets. So yeah, again, explore that when you want. But to recall, multi-maps are maps that permit multiple entries with the same key. So normally maps and sets only allow you to have one instance of each key. They don't allow any duplicates. Multi-maps do, but that actually gives us some weird syntax problems because that means we can't really have a logical sort of bracket operator or .at operator because they wouldn't know which value to return for that key. So instead, the way that we insert elements into a multi-map is using a pair. So this is another great example of where make pairs is super useful. In this case, it will automatically deduce that 3 and 3 are ints, and it'll insert it correctly. This is another way to insert things into a multi-map. That's actually not a pair right here. It's something known as an initializer list. So if you ever see the word initializer list in an error, you sort of know what it's referring to now. And then sort of key now, whereas with maps and sets, the .count function always returns 0 or 1. As you guys told me last lecture. In this case, for multi-maps, now it can return greater than 1 things. Cool, so bringing us back to map iterators. Again, just bringing up sort of this one edge case, they're actually slightly different than other iterators and containers because whereas other iterators, when you dereference them, they'll give you sort of a single object, sort of a vector of ints. When you dereference an iterator to that, will give you an int, and so on and so on. Dereferencing a map is the special case where it actually gives you a pair. So the way that you would use a map iterator is something like this. So again, we can just declare it using our usual begin and end. Notice that, again, we are sort of comparing using the not equals and incrementing it using the plus plus. The one difference here is that when you dereference it, you can't just use it immediately. You have to use either the dot first or the dot second, where the dot first corresponds to this first int value and the dot second corresponds to the second. Does that make sense to everyone? Does anyone have any questions? Okay. All right. And one other thing I wanted to highlight is that actually the placement of these parentheses is super important. Because of the way that sort of operator precedence is what it's known, sort of the order in which C++ will execute each of the different operators. If you don't have the parentheses, what it'll try to do is it'll try to calculate I dot first, and then it'll dereference it. But I, in this case, is just an iterator, so there is no concept of dot first or dot second. So, sort of fun fact, another common syntax that you might have seen is the I arrow second or I arrow first. That's a shorthand for this parentheses dereference dot. And all of that will likely become more and more familiar to you as you take 107 and other classes, because it's the same syntax for pointers as well. Yeah.
So this basically prints out the key and the values for every.
Yes. Yeah, absolutely. That's a good translation. So what this example is doing is printing out every key and value in the map. Yeah, very nice. In sorted order based on the key. Awesome. Cool. So just to give a sort of sneak peek into how cool iterators are, here's a couple more uses. So again, so far we've only been, exactly, like printing out all the values across an entire data structure. So let's see what else we can do. Oops, actually, before we do that, I forgot to put this slide in. Here's just sort of like a brief example of map iterators. So again, what this example is we're taking the same example from last time. You'll notice we have our get line, and what we're doing is we're reading in a response and sort of creating a map of how many times each word appears. And last time, all we were doing was just sort of then accessing the map and seeing whether it's there or not. This time, what we're going to do is sort of similar. All we're going to do is just print out everything that's in the map. And so that'll be exactly what that lecture slide was. So it'll be something like, again, the first thing we need to do is create an iterator to the beginning. So that'll be type iterator. Type begin equals, let's say that one more time. Yes, thank you. Yeah. Nice. Yes, good catch. And then again, sort of, there's two ways we could do it. I'll do it this way. So let's say while let's call that iterator doesn't equal freak map.end. Then what we're going to do is we're going to see out, and again, this is just demonstrating that we have to use this dot first, so see out it dot first, it dot second, and then, perfect. So let's try running that. Good catch, you guys. Thank you very much. Wow. Oh, man. You guys are on top of it. I can't even make the joke that it was intentional because that was great. Okay, so let's do something like that. And perfect, it does as we expect. So I mainly put this here so that you guys can sort of play around with the program as you wish. But does anyone have any questions about that so far, about the map iterators? Nice. Oh, Avery has a question.
Can you do a range-based for loop?
Oh. Yeah, can you do a range-based for loop over a multi-map? Over a multi-map or a regular map?
A map.
Over a regular map. Yeah, absolutely. So again, sort of just like last time where we could, instead of doing this for loop over the entire map using iterators with a set, now we can do the same thing for a map, where instead of using iterators, we can do something like for, in this case, the type of each element in a map is actually, again, a pair. So it's a pair of string and int. But that's a little annoying to type, so instead I'll just write auto. So for auto element in the frequency map then all I want to do is cout. In this case, again, because element is a pair, you still have to call sort of element.first and element.second. If you try and see out just the elem, I forget what happens. It'll either throw an error or it'll print out sort of the default pair. So let's see. Let's try that. Ooh, perfect. All right, and actually that's a great point because it sort of goes back to this point of like, oh, okay, so we don't really need iterators here, so what do we need iterators for? So let's explore that iterator uses.
Can I also just mention one more thing? I actually just learned this a couple weeks ago. You can actually use structured binding inside the object.
Oh, yeah. Yes. So structured key val, and then cout. Key and cout val. Very cool.
Yeah, because I know it's really annoying that you have to keep typing like the item.first, item.second, so you can just unpack it directly inside the for each loop.
Yeah, that's actually a really good point. And that's a nice feature about the pairs as well. Nice. Okay. All right, so another thing I wanted to do with this lecture in particular was sort of give you a taste of building like how you would write a program from scratch. In this case, our program won't be doing much. It'll be sort of just doing a couple different examples, but this way you can sort of see how you might approach it yourself. So the first thing that we want to do, of course, we just basically the three things that we'll be doing is we'll be sorting a vector, finding an element, say from a set, and then we'll see from there. We'll see what we want to do. So let's just declare our own vector, a vector, and of course, if we want to declare a vector, then we need to import the vector class. So we're going to include vector. And then because I don't want to write std vector everywhere, I'm going to say using std vector. Perfect. So now let's say I have a vector of ints. And again, uniform initialization. So I could do like random numbers. And then let's see. All right. So let me define really quickly a function called print vector, which will take in some sort of vector. So remember, sort of you should have learned in 106B or in other classes, because we're passing in sort of a significant data structure that's more than just an int or a bool, then we always want to pass it in by reference. And in this case, because we're not changing the vector at all, we're going to be passing it by const reference. So pass in a vect. Oops. And then we'll be doing, we can do our usual for auto for every element in B. See out that element, and then I'll see out one more time. Or actually. And also, I'll be posting all of this code after class, so don't worry if you don't type it all. Okay, so now we notice a couple of things. First, that cout and endl are complaining, of course, because what I need to include is the iostream class that includes both of those. So iostream, and again, I could just say using std cout wherever I use them, but that gets a little annoying. So I'll instead use using std endl. Perfect. No complaints so far. All right, so to sort a vector, really the key thing why, so actually here, we can test that it is correctly sorted so far. The key reason why iterators are gonna be so useful is how they work with things like functors and algorithms, which we'll actually go into in a lot more depth the lecture after next, but these are some basic algorithms that you'll end up using a lot. So let me change this to iterator uses. And perfect, prints out what we expect. Sort of classic example is something known as the sort algorithm. So all of these algorithms in the STL are found in this algorithm class, with the exception of a couple others that are found in the numeric class that have to do a lot with numbers. But in this case, how do you use the algorithm? It's an algorithm called sort. So if you can see right there, it'll actually tell you the parameters that it's expecting. In this case, it's expecting sort of a first iterator, a second iterator, and then the comparison function. So what we'll do is of course, what we want to sort is the entire vector, so vec.first, vec.end, and then we'll use the default comparison, which it'll figure out based on the type. So let's try that and see what happens. Perfect, and we see that it's sorted. So that's kind of crazy. If you remember, if you were here after class 2 lectures ago, I sort of showed the difference between traditional sort and then using this sort algorithm. And it pretty much takes something like 10 to 15 lines of complex code and turns it into this algorithm. And we'll be going over later, but really the STL algorithms have already been optimized to be sort of the most efficient algorithm for sort possible. So that's sort of another benefit that we get from using things like that. Okay, so if we wanted to find an element from a set, let's do the same. So we'll do a set of int, and again, if I want to use a set, then I know that I have to include the set library, and I also don't want to be typing std set everywhere, so I'll just use std set. Notice here I just typed the std sort because I'm only using it once. So let's see, we'll call this elements, and then we'll do the same, 3, 1, 4, 1, 2, 6. Quick question, how big do you expect the size of this set to be? How many people think that it will be 1, 2, 3, 4, 5, 6, 7, 8, a set of size 8? How many people think it'll be a set of size 8? Okay, how many people think it'll be a set of size less than that? Okay, what size do you think it'll be? You right there. What's your name in the glasses? Oh, I guess this is where it's helpful to know his name. Oh yeah, what's your name? Yeah. Say that again? You? Right. Okay, you. Yeah, what size do you expect it to be?
I'd say
1. There we go. Yeah, exactly. So sort of tricky question. This is just to show that even if you initialize it with something like duplicates, once it creates the set, it'll always remove those duplicates. So we can see out elms.size. Perfect. Awesome. Okay, so sort, really common one. Another really common algorithm that you're going to see is something known as, let's say we want to find the element 5. So actually last time, the way that we determined whether an element was in a set was using this function elms.count. And then that would print out, it's found once in that set. We can actually do the same thing but using iterators instead. So the way that would look like is, again, using this std find function from the algorithms class. And here we see that it expects a first iterator, a last iterator, and a value. And so, okay, our first iterator will be elms.begin. Our last iterator will be elms.end, and then the value we want to find is elm.toFind. And when we say sort of for good style in assignments use things like constants, that's sort of exactly the thing that you'll be using, is a global constant like that. Perfect. So if we then print out, let's say, if the way that we use the find function is it'll either return an iterator pointing to the location of that element in the set, or it'll return the end iterator if it's not found. So we'll say, let's see, so if auto test iterator equals that, so if the test iterator equals elms.end, then we know that it's not in the set, so we see out not found. Else, if it is in the set, then we will see out found, and then we'll dereference test iterator. So let's see if it does it correctly. Oh, perfect. And it says found 5, which it is indeed in the set. And elms size is 7. Yeah, what's that? Yeah, that's a great question. Exactly. So elms.end does not actually point to anything in the set. It points to the last element plus 1, so it's outside of the set. Very good question. Yeah. Any other questions so far? I guess one thing to point out is just sort of how easy it is to use these common functions. So things like sort, things like find. Okay, sort of the last thing I want to show as just an example of how versatile iterators are. So up to this point, we've sort of always been iterating through the entire vector or the entire set. So one thing is that in here, instead of saying vector.begin or vector.end, we could say sort just the first three by doing something like vector.begin and then vector.begin plus 3. So let's actually take a look at that right now. So instead of that, let's just sort the first 4. And then we'll leave the rest of them unsorted. And perfect. It looks like just the first 4 are sorted and then the last 4 stay the same. Another thing that we can do is actually, even when iterating over a set or something like that, we can actually use, actually iterate over ranges of the data structure instead of the entire data structure. So the way that you might do that would be something like taking a set of integers, and let's create some new iterator. Let's see. And this is a function called lower bound and upper bound. So the way that lower bound and upper bound work is lower bound finds the element that is either equal or greater to the given element. So in this case, it would find 4, because 4 is the smallest element that is either equal or greater to 4. In the case of the function upper bound, sort of misleading actually. It sounds like it should do something similar. It sounds like it should do something the opposite of lower bound, but it actually does something very similar. So whereas lower bound, let's do 6. So whereas lower bound will find the smallest element greater than or equal to the passed in element, upper bound will find the smallest element strictly greater than the passed in element. So small difference right there. It can be slightly confusing, so you can think about that a little more. But we can sort of, let's print out, let's see, our start is going to be the number, whatever that is, and then our end will be the element of end. And then then we can do from here sort of all the things that we would have done before. So this is sort of where the for loop that is not the for each loop actually comes in handy. Because with the for each loop, it automatically does it over the entire container. When we use just the regular for loop, we can sort of control what parts of the container we want to do it over. So in this case, we'll have some sort of iter. And notice that since we've declared it already, we don't need to initialize it in the first statement of the for loop, so it'll actually be empty. The second one will be while it doesn't equal to the end iterator, and then finally we'll increment our iterator. And then from here we can see out, see out iterator. And then, so let's see what that does. Oh, perfect. So notice that in this set, what it did was it found the lower bound of 4, which is 4, and it found the upper bound of 6, which is 9, because 9 is the lowest number that is strictly greater than 6. And then when printing it out, it never includes the last iterator. So in this case, it'll print out 4, 5, 6. So sort of cool. A bunch of different ways to now play with your data structures, regardless of what the data structure is. We could have easily replaced set with vector, and all of this code would have still worked. And yeah, so this is sort of like building up our toolbox. And then when we talk about functions and algorithms, we'll really learn about sort of common ways that these tools have been used already. Awesome. So just to recap what we did, once again, we have sorted using the sort algorithm. We found an element using the find. And notice that we talked about something similar last time. So last time, we talked about this method of finding whether a key is in a data structure using the count method. In this case, again, with a mapper set, it'll only ever return 0 or 1. And so if we check whether it's equal to 0, then we know that it's not found. It turns out that there's another way to figure out whether an element is contained in a mapper set, which is exactly using this find function, which now you guys know because you know what iterators are and how they work. And so this is another way to check if something is found or not. It looks a little longer. It turns out that find is actually ever so slightly faster than count because count is implemented just using find. So if you really, really care about that difference, you should feel free to always use find. Even though it looks longer, it's actually slightly faster. And then, of course, the most important note is that in C++20, you won't have to worry about any of that because they're finally coming out with a blessed contains key method. Awesome. And then finally, the last thing that we discussed are iterator ranges. So using functions like lower bound or upper bound to sort of isolate ranges within your data structure, within your sorted data structure. Just as a reference, you'll notice over here that iter and end have lower bound and upper bound or lower bound calls. These calls are the equivalent to those in math. So if you wanted to say get things from 5 to 26 inclusive, then you want to use lower bound and upper bound for your begin and end, and so on. Not really important, but just a nice reference because these can get sort of tricky to think about in your mind. Yeah, go for it.
Actually, today in our 106B section, we just got a handout for the syntax, and it already contains map.contains key.
Yes, so this is a difference between the Stanford and the standard libraries. So in 106B, the 106B map does have a contains key. Yeah, so these two are actually the equivalents of the Stanford contains key because the standard C++ doesn't actually have a method that looks like that, unfortunately. Yeah, so these are sort of workarounds, and then finally this year we'll actually get a sort of equivalent. Yeah.
What you'll notice about the Stanford library is like a lot of the functions, they hide all the iterators from you. You never have to deal with iterators in the Stanford library because that's what their goal is. They don't want you to have to deal with iterators.
Right, exactly.
So now we're like unpacking that, showing you like how you actually use iterators.
Yeah. So if you guys really want to throw your section leaders for a loop, you can bring up iterators, but not recommended unless after class. All right, and then finally, sort of the last thing we touched on was again, the idea of the range-based for loop, which is something that you do learn in 106B. And now you guys know how that works. It turns out if you actually go to the documentation for the range-based for loop, it is implemented exactly as we have learned about iterator for loop so far. So that's kind of cool. You've literally implicitly implemented your own part about the standard library. So that's pretty nice. Cool. So before I go on, does anyone have any questions about iterators at all? Yeah, Julie, what's up?
Is it considered more C++-ish to use the range-based for loop or to like actually set up your iterator?
Great question. Is it more C++ to sort of do this, or is it more C++ to use the range-based for loop? So when you're iterating over your entire data structure, it is considered, I think maybe style-wise there's no strong opinion, but most people will just use the for each loop because it's so much nicer looking. Really, this one only comes into play either when you really need the iterator. For example, if you're going to be calling something like the sort or find function within here, or if you only want to iterate over parts of your data structure, not the beginning to the end. Very good question. Yeah.
I'll add on to that because you'll notice that the first loop is like much cleaner, much better looking. And and then you pick up a good difference, which is like the first loop is kind of restricted in that you have to loop over the entire collection, and that's actually a common concern among the C++ community. In C++20, they're actually coming up with this new thing called ranges, which essentially lets you modify in the for each loop. You can change what the range you want to loop over is. So right now, by default, the range is always the entire collection, but in the future you are able to like construct these ranges so that instead of going over every element, you can go over like every other element. You can go over the first half of the vector, etc. Yeah. So you bring up a really good point. That is a thing that C++ is working towards.
Yeah, that's good. That's a good point.
Yeah. If we have time, we might cover ranges. If we have time.
That's true. There's a whole bunch of really cool 20 features that we may or may not cover in the end. Cool. If no other questions, then a quick break for announcements. So first, office hours for assignment 1 have been released on Piazza. So if you guys have any questions, take a look at the Piazza post. We've both added additional office hours to the usual one after class. And if you can't make any of those times, feel free to message us because we'd be happy to meet up and find another time. The other thing is that, so we promised at the beginning of the quarter that you would have 3 chances to sort of create late days. This is the second one. It's just a feedback form in the middle. And this is where you can tell us things like, we're going too slow, we're going too fast. Things like, I have no idea what std : is still, and it's really bothering me, so I'd appreciate it if you took 5 minutes. But although I promise that we'll learn about it later. Anything like that. So we'd love to hear from you guys. Feedback form responses are going to be anonymous. So once you've submitted the form, there will be a link where you can then add your name to show us that you've completed it. So feel free to do that by next Thursday, and then we'll sort of incorporate your feedback so we can make the class better.
Yeah, the form is really short, so please do fill it out. Please help us out.
Yeah. Cool. And then one other thing I wanted to do was just really quickly to get you started on some of the syntax of assignment 1, which tripped a lot of people up last year, is a quick review of structs. So again, this should all be review. You should all be familiar either from 106B assignments or from reading this assignment. Again, a struct is sort of a way of bringing together a whole bunch of different types of data. The way that you initialize it is, again, using this uniform initialization. And then the way that you can access this sort of feels like a pair. You can access it by the name of that piece of data within the struct. So object.var1 gives you some new value. Again, this is all in the slides. Turns out in C++, the struct keyword is optional when you're declaring something. In C, it is not. So in 107, you always want to use the keyword struct. Okay, this is for the assignment. So again, in the assignment, you'll see a couple of different structs. One is the simple graph struct, one is the node, and one is the edge struct, which isn't shown. And I just really quickly wanted to get people started on the syntax of this. Again, to declare a simple graph, actually the uniform initializers are optional, but just in there for reference. Really quickly, based on the struct syntax that we just reviewed, talk with your neighbor and answer the question, how would you add a new node? Let's say the values are x1 and y1. How would you add a new node of values x1 and y1 to the simple graph vector of nodes? What would be the syntax for that? So just think about it to yourself and then take 30 seconds and exchange it with your partner and see if you came up with the same thing. So again, we have a simple graph, and I want to add one node to this vector of nodes in the simple graph. What's the syntax for that?
So a reminder for next time, have them on before.
Oh.
Have them on before, yeah. Right now, that's kind of.
Did you say simple graph is vector?
Simple graph is a struct. Yeah, simple graph is this struct, and that struct contains a vector of nodes and a vector of edges. Yeah, that's a good question. And it is sort of convoluted, which is why I wanted to bring it up in lecture. Yeah. How would you do this? And this is what you'll be doing on assignment 1 if you do it. Okay, does anyone have any thoughts? Any ideas? Yeah, go for it.
We will do simple graph dot node, so we'll access the vector nodes basically,
Perfect.
and plus equal to node.
Okay, so this is a great idea in the front. So I heard we're gonna do the simple graph. So in this case, the name of the variable is graph dot nodes to access the nodes vector, and then add using the plus equal to add a node. So one reminder is that actually the plus equals doesn't exist in standard C++. So what we'll have to do instead is use the dot pushback. But that's exactly the right idea. So exactly. So we take our graph variable, access the vector of nodes using dot nodes, and then we push back to that vector within the simple graph using the pushback function. And then again, using the uniform initializer to create the x and y values. Does that make sense to people? If that makes sense, then sort of I think you have you'll get a good start on how the assignment is structured. Okay, I'll just leave that in the slides, and you can take a look at that again. Cool. Okay, so there are a couple of things that you might have noticed in our iterator example before. Oops, sorry. So one of them is, you'll notice that up here, when I said that I wanted to sort say just a range of elements in my vector, you'll notice that I did something that's sort of unique. I did vec.begin plus 4, which sort of intuitively makes sense. It's saying, okay, I want the pointer that points to this 3, or iterator that points to this 3, and then I'll just add 4 to it, so it should point to this 5. And that's exactly what we saw. But this operator isn't actually something that we've discussed before. Up till now, we've only ever discussed the plus plus operator, which increments it by 1. Let's see what happens if we try and do this same thing for a set. Again, sort of in our minds, it seems reasonable. I have, so let's say instead I was doing something like, let me just quickly comment the rest of this out. In a set, I had something like std sort, lms.begin, lms.end, and then I'll just do for elements. And I'll just do it after. And again, for good style, I would have definitely decomposed this. And actually, on Thursday, again, sort of, this is an example of why templates are so necessary, is that this is exactly the same code as this. The only difference is that this is a vector and that's a set. So next lecture, you'll learn how to use the exact same print function for both. So cool, neat heads up. But we can take a look and see what it does. And it actually complains already. So this gets us to our next topic, which is Iterator Types, but sort of the intuition to why this is an error, even though this isn't, and we can even change that back to vec.end. Why is it that this works and this does not work, even though they're both different containers? It turns out that sort requires something known as a random access iterator. Because of the way that it implements the sort function, it needs to have this ability to just jump around arbitrarily anywhere in the container. And it turns out that sets, even though to us they seem sorted, because they aren't sorted under the hood, you can't actually call this sort function on them. So that brings us to sort of, okay, so then how do I know when I can use something versus when I can't use something? I guess the last thing I want to raise is you'll notice when I typed std sort and we took a look at sort of these, it telling us what the templates were, it's hard to see, and it doesn't increase. But you'll notice that here it says random access iterator, versus when we did something like std find earlier, right here all it says is input iterator. So that's sort of that'll tell you what sort of iterators that it requires, and then now we'll learn what are those different types of iterators. So iterator types. So far, we've really only incremented them using plus plus, but for some things, like a vector, it makes sense that we would be able to do something like, okay, add, say, the size divided by 2 to that iterator. And same with the deck. Seems right. Seems like that should be something we should be able to do. The problem is, for something, say, like a set or like a linked list, where a linked list, if you're not familiar, looks vaguely like this. And if this looks foreign, don't worry about it. But the idea is that you can't get to the next element until you've sort of traversed the previous ones. The only way you know where to go next is by looking at the previous one. So in that case, it doesn't really make sense to do something like mylist.begin plus 3. Because to go to that plus 3, it's not just a matter of like adding the number 3. It's something like you have to follow the arrow 3 times, in which case you're really just doing .begin to .end anyways. So how does C++ resolve this? And again, you'll get sort of, the unfortunate part about this is that you'll get really obscure error messages. So this error message, it's sort of like invalid operands, and you really have no idea what it means by that. But what that means is really just that you're using the wrong kind of iterator. Exactly. So what's going on? Turns out there are 5 different types of iterators. And no worries, because for each type of container, it's really well defined what kind of iterators they are. So this is just to sort of get a feel for when you can use each type. And this is sort of a preview. It turns out random access is the most powerful, input and output are the least. And you'll understand exactly what that means in a couple of minutes. So first, things that every iterator can do are those 4 sort of basic functionality that we introduced at the very beginning of this lecture, which is that they can be created from existing iterators, they can be advanced using plus plus, and they can be compared. And we saw all of that at the very beginning. What is an input iterator? So an input iterator you can think of as, say, like an iterator that would be used for an input stream. So there's two characteristics. First is that it's input only, meaning that you can only ever read values from it. You can't ever write something to that iterator. In other words, it can only ever be dereferenced on the right side of an expression. And the second is that it's single pass. I'll get into that a little later, what that means versus multipass. Turns out, again, we've seen these already. I just showed you in the find function, all it requires are input iterators. So as long as you have something like an input iterator, you can use find. That means with something even like a stream, like an input stream, you could actually use the find function, which is kind of cool. And then there's also things like, and same with count. Again, only requires the input iterator. Yeah, same with input streams. Output iterators. Exactly like input iterators, the only difference is that they're write only. So you can't ever read the value from an output iterator, you can only write things to it. So yeah, they can only be dereferenced on the left side of the expression. Again, you'll see things with like this with output streams, like output streams or cout, as well as this function called copy. That's another algorithm that you can take a look at, which will copy an entire data structure into another one. Okay, so forward iterators. Forward iterators can do everything an input and output iterator can do, and have the additional functionality of being able to make multiple passes. So because of the first, it can do everything an input and output iterator can do. That means that it can both read from, like it can here, and write to iterators. And then the last part is making multiple passes. What that means, essentially, is that if you have two iterators pointing to the same thing, so you have some iterator A and some iterator B, if you plus A and plus B, those plus pluses are guaranteed to again point to the same element. So for example, if you think about a vector, if you plus vec.begin, and then you create another vec.begin and you plus that, they're guaranteed to be the same first element. Which seems sort of intuitive, but then if you think of something like, say, an output stream or an input stream, say we have cin and you plus on cin, then if you call, say, cin.begin, which isn't exactly it, but sort of mentally that's the intuition, then it'll actually point to this. So if you plus that, these two won't be the same. That's sort of the general idea of what the passes are. And I will say at this point, I'm giving you all these details just so you sort of know what's going on. Really, in real life, when we use these different types of iterators, all you need to know is that it's whether something is a forward iterator, an input, or output, based on the documentation. The documentation will tell you what kind it is, and that way, that's how you'll sort of know when you can use each one. So if the passes things sort of passes out of your memory, no worries about that. Unintentional pun, that's great. The other thing that I want to point out here is that the reason why there are these arrows here are because each of these is sort of a superset of the previous one. You'll notice the forward iterator is a superset of the input and iterators plus some additional things. What this means practically is that if there's a function, say in this in the find where it requires an input iterator, it means that you don't have to give it an input iterator. You can give it an input iterator or anything more powerful than it. So in other words, it would be sort of useless if, say, a vector only had random access iterators and then you couldn't use find on it. So yeah, again, practically, you can use anything that's more powerful than the required thing.
If you learned about inheritance in your previous class, this is basically an inheritance hierarchy. Yeah. Every random access iterator is a bidirectional iterator, and all bidirectional iterators are forward iterators.
Yeah, sort of like squares and rectangles, if you've heard that. All right, yeah, what's up?
So what you were saying before, if you made two input iterators and pointed them to the same element and incremented one of them, both of them would move forward? Is that what you're saying?
Yeah, that's a good question. So not quite. So let me explain that more clearly. So with an input iterator, say we created an input iterator to one point and another input iterator to that same point. When you plus each of them, they're not guaranteed to go to the same location, which is kind of odd. But a way to think about that might be something like an input stream, where once you plus plus something, it's been like consumed. So if you plus plus something else again, there's sort of no logical, it's sort of almost undefined behavior. Like, would it go to the same thing? Would it go to something new?
So even though they're two separate instances of iterators,
Yes.
the behavior of one affects the behavior of the other one?
I would think about it. I think that's one way to think about it. I think a clearer way to think about it might be that plus plussing each of them independently doesn't give defined behavior. Like, it could be that they both go to the same thing. It could be that the operating system just arbitrarily makes them go to something like two things later.
Also, so for input iterators, you can't make copies of input iterators. You can't make two input iterators.
Yeah, so you can create them both again, but you can't copy one from another. In case that also helps clear things up.
So, sorry, just last clarification. So
Yeah.
does that mean that there can only ever exist a single input iterator for a given container? Otherwise, there's undefined behavior?
That's a really good question. So that actually gets into the topic of when do iterators become, when do iterators become invalidated? So that's actually a really good question. I'm going to table it. I think Avery is going to talk about it at the beginning of next lecture about when do iterators become invalidated. And I would have to look it up actually again for input iterators. My belief is that may be correct, but we will confirm with that when we talk about it next lecture. Yeah. So that's a good question. What's up, Tim?
Is the type of iterator defined by the container you're iterating over, or can I explicitly say I want a for iterator or I want an input iterator?
Great question. So the most powerful type is defined by the container. So a vector will define that its iterators are, and we can actually take a look at that if we look at something like, let's say it's the vector CPP reference. If you look at the documentation and look at something called the member types, you'll notice that there's a member type of iterator, and that will actually tell you what is the type of iterator, that sort of thing. So it's defined with the container. As to whether you can declare, say, a vector iterator, random access iterator as an input iterator or a forward iterator, that goes into the idea of inheritance. So inheritance is a full lecture because it's so tricky. We're actually not likely going to teach it this class, but we'll give it as an option for the final lecture where we let you teach anything. So yes, theoretically it's possible. There's just like a lot of like buts in that statement. Yeah, tricky things. Good questions. Okay, so that's forward. Almost done. Last two. So bidirectional iterators, again, everything a forward iterator can do, plus it has the decrement operator. So the forward iterator, even though it could plus even though it had multiple passes, it couldn't ever go backwards. So yeah, bidirectional iterators, you'll see that with functions like the reverse function, which you can pass in something and it'll reverse every element in it. Actually, bidirectional iterators are what the map and set classes define. So that's why we couldn't use the sort function, because the sort function required a random access, which is more powerful than the bidirectional ones. It's also what the list defines. So linked lists, also only bidirectional. And then finally, random access. These are the most powerful. And these are the ones where you can increment or decrement using arbitrary amounts, like 3 or half of the size, things like that. And those are what vectors, decs, strings all define. It actually turns out pointers are also a type of random access iterator. So that actually covers all of our 5 types. Does anyone have any questions? If not, then one last word I want to say. The difference between pointers and iterators is slightly confusing. It seems like, and so this is mainly if you've learned about pointers before and are trying to figure out how iterators fit in with the idea of pointers. You can think about pointers as sort of a class. Pointers are like a specific class that you can declare, like a void star pointer or something like that. Iterators, you should think about more as like an interface. Iterators are more like a set of promises. So a random access iterator promises that you can increment or decrement your finger by arbitrary amounts. What that means is sort of like, you can think about pointers as just being one implementation of a random access iterator. And then similarly, sort of with the vector iterators and things like that, they're all implementations of the random access iterator. Yeah, awesome. We will see you next Tuesday with templates in that case. Super powerful, so super exciting. And don't forget to fill out the feedback form because we'd love to hear from you. But good job, everyone.
Of course. All right. Thanks. Yeah. So I'm just like.